We're going to finish up chapter 13, covering Kepler's laws. Alright, so Kepler has three laws about planets and satellites. A planet is obviously going to be the object that something is orbiting around, and the satellite is the thing that's orbiting. So it could be a satellite orbiting around Earth, or it could be something like the moon orbiting around Earth. Or it could be something like the Earth orbiting around the sun. So Kepler's first law says that all planets move in elliptical orbits with the sun at one focus. So in the figure it shows that a planet of mass m is moving in an elliptical orbit around the sun. And they're showing you here it's exaggerated just so you get the feeling for what the different variables mean. In most cases, the orbits are going to be much more circular, but they are elliptical at least a little bit. We measure how elliptical something is, basically how much it deviates from being circular, by something called eccentricity, and we just use the lowercase e for eccentricity. Okay. Alright, so the sun, which is of mass big M, is at one focus of the ellipse. The other focus is F prime, which is somewhere over here, and there's nothing there. There's not a planet there. It's located in empty space, as it says. So each focus is going to be a distance of EA from the ellipse's center, with E being the eccentricity of the ellipse. So if you multiply the eccentricity times A, which is the semi-major axis, so A is called the semi-major axis. And basically what it's marking is from the center of the ellipse to the furthest point away. Right? Basically, the long way through the ellipse is going to be your semi-major axis. Right? And then conversely, the short distance from the center to the edge of the ellipse is going to be B, which is your semi-minor axis. Okay, so the semi-major axis A of the ellipse, the perihelion, which is the nearest to the sun. All right, so this is going to be the radius of the perihelion, basically from the sun to the edge of the ellipse, which is a distance rp, and then the aphelion, which is going to be the furthest from the sun. All right, so your aphelion radius, as shown here, is going to be from the sun all the way to the other edge of the ellipse. All right, and that's going to be given as Ra. All right, so that's just a bunch of different terms that we use when we're talking about an ellipse. All right, now Kepler's second law says that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is, the rate, which is dA dt, at which it sweeps out an area A is going to be constant. So basically what it's saying is, as a planet is orbiting the sun, in this case, the area that it's going to sweep out is going to be the same in the same amount of time. So let's say, and I'm going to try to exaggerate this a little bit, but let's say you travel from this point to this point, and then from the second point to this point in the same amount of time. This area swept out, shown here, so this would be the area of the first, and then for the second one, this would be the area, all this area in here. These areas are going to be equal. So basically what that's saying is, the further away you are from the planet or the star that you're orbiting, the object that you're orbiting, the further away you are, the slower you're going to go, because you're going to be sweeping out a lot of area. So if you think about it, if you're over here, you need to actually move pretty quickly, right, to encompass the same amount of area that was swept out over here. All right, so really what it says is an object that's traveling in an elliptical orbit around something like the sun is going to be, its velocity is going to be going very quickly over on this end and very slowly over on this end. All right, and all satellites, all objects that orbit another object are going to experience this type of movement. All right, so that was the first picture. The second picture is showing you the momentum. So the linear momentum of the planet and the components of P. So if we have a planet over here, we know its linear momentum is going to be in the direction of motion. Part of that momentum is going to be in the radial direction, and part of that momentum is going to be in the tangent direction. All right, so let's look at some equations here. All right, so we know that the amount of area that's swept out in some amount of time, and we're using the derivatives here because we're just saying there's a very small amount of area in a small amount of time, is going to be equal to 1/2 r squared d theta dt, and this is equal to 1/2 r squared omega, right? Because d theta dt is omega, right? And then you just have 1/2 r squared. So, so where did we get this from? Well, if we're talking about the area, and we can approximate this by just using the area of a triangle, because trying to figure out the exact area with this awkward angle over here might be difficult. So we're going to approximate it as it's shown, like with an area of a triangle. So the distance that it's traveling here, which basically would be the base of the triangle, this little distance here, is going to be the radius times theta, which is the angle it goes through. So this is just going to be r times the change in theta. And then, of course, the height is going to be, you can just simplify that as being the radius. So know that the area of a triangle is going to be 1/2 base times height. So really the area of a triangle is 1/2 the base times the height. So that would be 1/2 times the base, which is going to be r delta theta, right? R times the change in theta, times r, which is our height. All right, so that ends up, when you just simplify this out, this ends up being 1/2 r squared d theta. All right, and we want to know, and we're dividing the area by dt, so we take the derivative of that. All right. So we have what this change in area is going to look like in terms of the radius and the speed, right? The angular speed. So we can also look in terms of angular momentum here. So the angular momentum of this object is going to be simply r times the linear momentum, the tangential component of the linear momentum. Right? We know that it's actually r cross p. But if we just look at not the tangential, but the perpendicular component to this triangle, then we can figure out what the angular momentum is going to be. All right, so really this is the angular momentum of r, and then we know our linear momentum is m times v. So this v is going to be in the perpendicular direction, right, as shown here, this perpendicular part. Basically, it's this vector times the sine to get this, times the cosine to get this piece right here, if you knew what this angle was. And we can simplify this even further, change it into angular terms. So this is going to be r times m omega times r, right? Because the velocity, the linear velocity is omega times r. All right, so this angular momentum is then the mass times r squared omega. Okay, so now we have two terms that have this omega r squared in them. So what we're going to do is combine these two together. Remember, this is dA dt is equal to all of this. We're going to solve both of these equations for r squared omega and then combine them, right? Which effectively gets rid of r squared omega. So this is dA dt is equal to the angular momentum divided by 2m. Okay, so we end up with this final equation. So we see that basically the area swept out in a certain amount of time, which is shown by this term, is equal to its angular momentum divided by 2m, right? 2 times the mass of the object. This would not be the mass of the sun, this would be the mass of the object. Okay. Now, Kepler's third law is probably the one that's used the most. All right, it's called the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. All right, so basically what this is saying is the square of the period. All right, so we know that t is our variable for period, which is the amount of time that it takes to go around a full revolution. So the square of that is going to be is proportional to, it's not equal to, is proportional to the cube of the semi-major axis. So it's proportional to the semi-major axis cubed. And again, if we go back real quick, our semi-major axis is the distance from the center of the ellipse all the way to the edge that is nearest well, either edge actually, but it's the distance from the center to the edge of the ellipse, right, when you're looking at it longwise. Okay. Now, consider a circular orbit with radius r. The radius of a circle is equivalent to the semi-major axis of an ellipse, right? So if you just had a circle, this would be your semi-major axis, which is equivalent to the radius. Now, applying Newton's second law to the orbiting planet yields, so we know that Newton's second law is F is equal to ma, so mass times the acceleration. Well, this force here is the force due to gravity, and this acceleration here is the centripetal acceleration, right? It's what's keeping it in orbit. So we can call this force due to gravity, which we know from our previous lesson, as gmm over r squared. And on the right side, we have mass times this centripetal acceleration, which is what's pulling it in, right? It's essentially the acceleration due to gravity. It's what's holding the object in this kind of circular motion. Well, the centripetal acceleration can be written as omega squared r, right, as we've seen before. Okay. Well, so now using the relation of the angular velocity omega and the period, which is, so omega is 2 pi over the period. So we're going to plug this in for our omega here. So what you end up with is gmm over r squared is equal to little m times omega squared. So this is going to be 4 pi squared divided by t squared times r. And first of all, we can go ahead and cancel some things out. So we can go ahead and cancel these m's out, right? The mass of the object. So the mass of the object doesn't matter. No matter what the mass is, it does not affect the period of the orbit. All right, so we can then go ahead and solve for t. So if we solve for this t down here, we get t squared is equal to 4 pi squared. We have an r over here, and then we're going to move this r squared over because we move this t squared over here. So this ends up being r cubed and divided by g big M. And the big M's left. So we're going to divide these over to the other side. All right. Just to rewrite this in a different way, this is going to be t squared is equal to 4 pi squared divided by gm, which is all constant, times r cubed. All right, and like we said, this r is similar to the radius, or the r is the radius, so that's similar to our a value, which is our semi-major axis. All right, so this shows us that t squared is proportional to a cubed, which is Kepler's third law. Okay, so this table here just shows you some the period of certain planets as they're going around the sun. The period is shown in years, or Earth years, right? So Mercury goes around the sun in 0.24 Earth years. Venus goes around the sun in 0.61 Earth years. Earth goes around the sun, obviously, in 1 Earth year. All right, so on and so forth. And they go ahead and show you this relationship of t squared divided by a cubed because we know that they're proportional to each other, and we see the values are very similar all the way through. Right? Okay. All right. So last topic we want to look at is going to be the energy in these orbits. So as satellites orbit Earth in an elliptical path, the mechanical energy E of the satellite remains constant, right, as it must. So assume that the satellite's mass is so much smaller than the Earth's mass. The potential energy of the system, so basically we're just really looking at the potential energy of the large mass, right? So the potential energy of the system is going to be given by the equation we had for potential energy. So U is equal to gmm over r. Sorry, it's a minus. Don't forget the negative sign here. All right, so for a satellite that is going to be in circular orbit, the force of gravity is equal to our centripetal force. And this is kind of the trick that I used earlier. I said this force of gravity must be equal to the centripetal force because that is what's keeping the object in this circular motion, right? The force of gravity is the centripetal force, basically. right, so we can plug in our equations for each of these. We know the force of gravity is gmm over r squared, right, is equal to, and then we know the centripetal force is just mass times acceleration, and our centripetal acceleration can be written as v squared over r. All right, so we end up with this relationship. Now, we also know that our kinetic energy is 1/2 mv squared. Right, so kinetic energy is going to be 1/2 mv squared. And if you notice, we can sort of simplify this a little bit so that we can get something that looks like 1/2 mv squared. All right, so the first thing we can do, of course, is get rid of these r's. These r's go away. And what you end up with is gmm over r is equal to mv squared. So to get this right side into 1/2 mv squared, all I would have to do is divide by 2 on each side. Okay, so then I'm going to take this and plug it over here, right? Because that's going to be the kinetic energy. So the kinetic energy is just 1/2 gmm over r. All right, or simply I could write this as gmm over 2r, right? So this is our kinetic energy. All right, so we found what our kinetic energy is equal to. So for an elliptical orbit with some semi-major axis, the kinetic energy is also equal to minus 1 over the potential energy divided by 2. All right, and we can see that. We can see that just by comparing our kinetic energy, our kinetic energy to our potential energy, right? The only difference is it's divided by 2. So you take your potential and divide by 2, and you get your kinetic, right? And then put the negative sign, of course. Okay. All right, so I'm going to flip to the next page to keep going here. What we were looking at the total energy, which is E. So that's going to be the kinetic plus the potential energy. And we can say that's equal to what we just found. So our kinetic energy was gmm over r, or 2r, excuse me, minus our potential, gmm over r. And it's minus because there's a minus sign in front of the potential energy there. All right, so I can easily combine these two. So our total energy is minus gmm over 2r. All I would do is multiply this by 2 over 2. So you get gmm over 2r minus 2 gmm over 2r. All right, so that's going to end up with a negative gmm over 2r. All right, now if you compare this to, again, what kinetic energy is, which is right here, this is just the opposite of. So what you can say is our total energy is really just the opposite of the kinetic energy, right? The negative kinetic energy. So our total energy is equal to minus gmm divided by 2a, right? And I'm replacing r with a because it's for an elliptical orbit, right? And a is our semi-major axis. All right. All right, that is it for this chapter. We'll see you next time.